so I'm ready to go.
Okay.
I'm ready to
so,
start.
can you be the instrument?
Okay. Yeah. The last lecture in the mini course, and well, we are going to talk a bit more afterwards. Yeah, there are questions. What's for the next mini course? What's going to happen? Who is coming to visit us again? Rob definitely is coming, but other professors are also coming. So afterwards, we are talking about.
There is a test also again.
Yes.
Okay, well, thank you all for enduring to the end. What I want to talk about in this final session are the
There's a button. Turn on, turn off.
There is a button.
Right side, I think.
There. Okay. So, I want to talk about some of the frontiers of the subject. So, anybody of the age of 3 and up can do black hole chemistry. You know, you've got a good color-formed adventure set here. What I want to talk about are how these ideas might be extended to de Sitter space, where the cosmological constant is positive, or and a particular generalization that's more concrete, having to do with what I call cosmic solitons. And then I want to talk some about a new area that's developed, having to do with black hole heat engines. And then I'll finally say some things about the ADS-CFT correspondence and how this is connected here. All of these areas are new areas. The ideas and results are much less firmly established, much less is understood about them, so this is where new things really are to be found. Now, in some of the other things I talked about earlier, in these classes, there are some new things there, but these really, I think, are the frontier areas. So some of this work has appeared in these papers, and I'll give other references throughout. So, cosmic tension. What if lambda is positive? Well, the opposite of pressure, negative pressure, is what we call tension. Pressure of a gas, you push out. If the pressure's negative, you're pulling in. And so it's a kind of a tension. It's a resistance to getting pushed outward. So presumably, if this makes any sense, one should be able to look at negative pressure or cosmic tension. You can certainly calculate a volume using exactly the same methods as is done before, and you get a first law for a black hole where lambda is positive, and a Smar relation where h refers to the black hole horizon. And this is an integral at future infinity minus an integral at the black hole. But you also get a first law for the cosmic, or the de Sitter horizon. And now, the volume, instead of going from infinity to the hole, goes from infinity to the de Sitter horizon. But likewise, you can show there is a first law. Notice the sign changes here. That's because temperature is surface gravity, and surface gravity is positive at the hole, but it's negative at the cosmic horizon. And so since temperature is supposed to be positive, you get these minus signs here. But there isn't a whole lot of difference. So we constructed in this paper with Brian Dolan and David and Jenny and David Kubiznak the same kind of argument that I showed you earlier this week. You have a hypersurface evolving into the future along a time-like killing vector. You have a solution that obeys Einstein's equations, and you want to perturb the parameters nearby that solution. So the constraint equations are no different than they were before, but lambda is positive now. not negative. And you can show this same identity, it's exactly the same arithmetic. And so you end up getting this kind of equation, well, this equation here, just like a Gauss law. So now the difference is we have a black hole horizon and a cosmological horizon. Beforehand, we had a black hole and just some fictional surface that we could extend out as far as I like. But now we actually do have a two-boundary kind of problem. But nevertheless, there's nothing stopping you from doing a volume integral in between these two. And then you find you get the integral at the cosmic horizon is equal to the integral of the same thing at the inner horizon. By inner, sorry, I should say the black hole horizon. I don't mean a horizon inside the black hole. I mean the inside of the surface. So now, this, in some sense, you could argue is really the first law of cosmic mechanics. You've got surface gravity times a change in area of the hole, plus the magnitude of the surface gravity times a change in area of the cosmic horizon, plus the v delta lambda term, plus this rotational part. The angular velocity at the horizon minus the angular velocity at the cosmic horizon is 0. That's what you add. Now I've left out gauge charges, but you can put them in too if you like. They're exactly the same as before. So I would say in some sense this is really the first law of cosmic mechanics. And if you make this identification, you get these first laws where you've combined the two heat terms, one from the black hole, one from the cosmic horizon. And this just has to be true based on geometric arguments.
Why do you don't have mass?
Well, I'm going to get to that. I don't have it because I haven't gone to infinity. And by that Gauss law relation, I don't get any mass because I've got the killing vector generator at the horizon on both sides and there isn't a mass to pick out.
Can
But
you use these at any surface?
in principle, yes, you can.
There is nothing special about the rest.
Well, what's special there is outside the horizon, you no longer have d by dt being time-like.
Okay, so
It
you
becomes
call
space-like.
it infinite.
Yeah, so you would want to stop there. Also, the other thing is that both those surfaces, the surface gravity is constant, whereas that's not guaranteed for an arbitrary surface in the middle. So the volume is this difference between these parameters, and this is perfectly finite. You don't get an infinite volume. So now Andre's question, what about mass? Well, you can go to future infinity. There's nothing stopping you from drawing, from taking that surface right through the horizon and going out there. The price you pay is what you mean by mass. Well, if you mean mass is that which you get by doing this integral over this b quantity for d by dt, whether d by dt is time-like or not, then yeah, that's the mass, or rather this is the change in mass. It's infinite, so you can add and subtract a de Sitter version of that omega potential, add it to the mass, subtract it from the volume, so subtract it from this term here at infinity, and you'll get the black hole, and then this is like before. So how do we understand that? Well, a de Sitter black hole looks kind of like this. The Penrose diagram is like oopsie-daisy, like that. So people live here, right? We live between these two horizons. If you go in here, you die. If you go out there, you're lonely. So this conservation, let me do the de Sitter example here. So here's the de Sitter Penrose diagram. So conservation means the mass here is the same as the mass there. No change in time. The mass yesterday is the same as the mass next week. Well, out here, it means the mass here is the same as the mass there. Now these are space-like separated, but so you've got a conservation in space. And you might say, that's a stupid thing, what does that mean? Well, it means it's conservation in space. So what it means is if space aliens were able to go out here and they could compute the mass at a surface And these aliens could say, oh, I'm getting this for mass, and let's see, I guess they could do it there. So before the light cones exit, they could send a message to people here, and these aliens would say, we're getting M for the mass. And then these aliens would say, hey, those guys way over there got M for the mass. And so do we. So there is some, in principle, well-defined notion of conservation, and that's what I'm going to use. I got no better ideas. So that's what we call the mass, and from that you get the first law I put on a few slides ago and the Smarr relation. If you go from the cosmic horizon to future infinity, this is what you get. It's exactly the same thing. So you have conservation of mass from the viewpoint of insiders, or this, the aliens would use this law, the red law. Since theoretical physicists have aspirations to divinity, we can use both. All right, so let's look at Kerr-de Sitter black holes, and I saved the most painful thing for the last. This is the Kerr-de Sitter metric with rotations in every possible plane in an arbitrary dimensionality, and it is complicated. This metric was found by Pope and Page and Liu and one other person. Yeah, Gibbons, I guess that he was there too. So they found this multiply rotating black hole metric. The mu's are like polar angles. They're like the cosines of a polar angle. The azimuthal guys are the phi's here, and the mu's obey this constraint. So the way these solutions are found is to take a black hole rotating solution that you know, write sine theta equals mu, and then we use the mu coordinate, and then add in another mu coordinate that's the cosine, so mu1 squared plus mu2 squared is unity, and then write a metric that has the extra mu parameter, but you tell that metric you're constrained this way, and then you get something like this, and that's basically how they figured out how to generalize this thing. So, it's a mess, but it's workable. Just to show you, here there's one difference between the even and the odd cases. I'm just going to show you what you get for the parameters. So here's the entropies for both horizons, the quarter of the area. Here are the temperatures. G squared, for some reason, they like to call, lambda is d minus 2, I should have written this down on the slide, over 2L squared, and L is 1 over G. I don't know why they like to do it that way.
Because in H to the gravity is the coupling constant.
Yeah, okay.
So,
and then just to show you the volumes, so it's, you can calculate these things explicitly.
So the temperature is negative?
This turns out to be a positive number. The minus of this is negative. The surface gravity. This basically beats this. This is smaller. This is smaller than this term. For the odd dimensional cases, so let's see, notice the difference. Notice the mass here has this product of all those chi factors, and I know this is a ton to remember. Chi goes like, chi sub I is 1 minus a sub I squared over L squared, okay? So the mass has all those chi factors in it. Notice when I go to the next slide, you've got this extra piece in the odd dimensional case. So the two have to be distinguished. It's basically because in the odd dimensional cases, you have an extra azimuthal direction that you can't match with a polar one. So here again are the results. They're really basically the same as before. What makes them different is this stuff up here. This is a little bit different. So this is simply to show you that these things are calculable. And one might say, so what? Well, what about this reverse isoparametric inequality? I showed you it was violated for superentropic black holes, but what about these de Sitter black holes? Well, here's this normal isoparametric inequality. The reverse one for black holes has this the other way around. So for a Kerr, I can show you now why the reverse thing is true. Here is the volume for a Kerr ADS black hole. And I can rewrite this last term to look like so. Focus on the purple part. Okay? This AJ works out to be this quantity using what I showed you on the previous slide. So R, now, if you look at the volume and divide out by the area, this purple thing is what I call Z. Here's the division by the area. This term here is this term here. This term there is that term there. So it's 1 plus this mess divided by, there's 1 over area times this area here. So it works out to be that, which I can pull in this R over here and simplify this to so. Now this thing here is always, if I break up this fractional sum into 2 pieces, I can show, basically, I can exploit the fact that there is a product of terms that is always larger than this particular sum for these functional forms. That's where this comes from. And this quantity here, when you simplify it, turns out to be twice that same Z. So this now becomes a function of this purple thing. F at 0 is 1. That's easy to see because, and then df dz is positive, so that's what gave this reversed inequality. For all Kerr de Sitter black holes, it's that. But what about anti-de Sitter? Sorry, but what if you have the opposite sign when you're in the de Sitter case? Well, let's see. If I look at the black hole horizon, I do get R greater than or equal to 1. So what that means is the same thing as in the anti-de Sitter case. If you give me a thermodynamic black hole volume for a de Sitter black hole, the kind of black hole that maximizes the entropy is the Schwarzschild de Sitter black hole. No rotation. So that's exactly the same as the anti-de Sitter. But the cosmic horizon is backwards. If I look at the cosmic volume and put it in there, I actually get the other way around. And so I find if you tell me, you give me now a cosmic volume, what black holes can I put in there? What's the best or worst case scenario? The ones that are Schwarzschild de Sitter, the total entropy is minimized if there's no black hole, instead of maximized by Schwarzschild.
So you know, just to get this physics right. So if it's just pure de Sitter.
Yeah, it would have to be pure de Sitter. That is correct.
So then, if I have a black hole, it's like taking degrees of freedom from the cosmological horizon and build a black hole. What I'm trying to say, the entropy of pure de Sitter is the maximum entropy from all.
Yeah.
I mean, if I have a black hole, the sum of the black hole entropy plus the sum of the entropy plus the entropy of the cosmological horizon is smaller than for pure de Sitter.
Yeah.
Okay.
The black hole pulls in the horizon
Yes.
and makes it less area than it would be, but the horizon of the hole itself doesn't overcompensate.
Yes.
So you've got both the reverse, so the holes obey the reverse isoparametric inequality, but the cosmic horizons are the other way around. And I'm going to show you a manifestation of that in a simpler case in a short while. So what about, oh yeah.
Is there anything that happened for equal rotation parameters in this method? I remember that
Equal rotating de Sitter. Is that your question.
A equal to B, for instance, in this case.
Well, nothing. I'm not sure what you mean when you say anything happens. There's nothing different happens with the isoparametric inequalities. As for the thermodynamics, we don't understand what they are, so I can't answer the question. But what I want to do is show you that you can do this for the two-rotation charged de Sitter case, simply because we wanted to see what charge and rotation do together, and there are precious few examples. So this Chong-Lu-Chvedek-Pope solution actually works for a positive cosmological constant. Now, you would never do this if you were a supergravity person because you need a negative one. But if I had never heard of supergravity, I could just say, oh, well, I'm going to use this Lagrangian, but with the opposite sign, and this is an exact solution. It's sort of puzzling to me that no one has ever pointed this out before, but from what we could tell when we wrote this paper, no one had ever pointed this out. So I've got if the things in red are the opposite signs to the Pope, Lu, Fenich thing, Chong, you know, that paper. And you can show that SMAR and first law hold at both horizons for this thing. So this is at least a non-trivial check on the general formalism that I showed you. The parameters are so complicated here that, you know, it's not going to be a coincidence that it works. So I became curious as to how we could understand cosmic volume, and part of the problem in understanding it is that either you have pure de Sitter space, for which you can do very little, there's only one parameter, or you have a black hole in de Sitter space, in which case you're messing up black hole volume and entropy with cosmic volume and entropy, and it's not clear how to deal with them together. So what would be nice would be if you could have a solution that had a cosmic horizon, but was not constantly curved, and that's what these things are.
These are exact solutions?
Yes. So this is Rick Clarkson and I, about 11 years ago, found this exact solution to the Einstein equations in little d plus 1 dimensions. It's easier to use little d this time because of the nature of the solution. And the metric functions are surprisingly simple. F is 1 minus a to the d over r to the d.
Yeah.
And g is the de Sitter function.
How this is not singular at r equals 0?
Just slow down.
Okay.
So this is you don't get to r equals 0. So what happens in this metric? We call this the Iguchi-Hansen soliton because in the limit that L goes to infinity, g becomes 1, and this metric becomes a d-dimensional version of the Iguchi-Hansen metric. How many have heard of the Iguchi-Hansen metric? Well, I know all of you have. How many of you have a friend that has not heard of the Iguchi-Hansen metric?
Yeah, nobody knows what the Iguchi-Hansen metric.
Okay. It doesn't matter. Iguchi and Hansen in the 1970s found a solution to the Euclidean Einstein equations that was self-dual. In other words, if you took, suppose I live in a world where I have plus, 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 time x, y, z. All time is like another spatial coordinate, it's Euclidean. Now, what they found was that if you demanded this condition, epsilon mu nu rho sigma, epsilon alpha beta gamma delta, r rho sigma gamma delta, if you said, I want this to be true, you can find an exact solution to the Einstein equations, and it looks like this when d is equal to little d is 4 and L is infinity. And that's why we call these Iguchi-Hansen solitons. Why solitons? Well, let's look at these functions. Let's suppose that, let's go let's suppose R is less than L, and we're going to make R smaller and smaller. Well, eventually R is going to equal A. Now, when R equals A, nothing interesting happens here, but this vanishes. So this vanishes and that vanishes. This is an angular coordinate. If F were 1 and G were 1, then this would be the what we call the fibration of a circle over a sphere. And if D were equal to 4, this would be a 3-dimensional sphere. Provided you properly identified this coordinate. So now what happens, if I use this function, is I get a different identification of that coordinate in order to ensure that I get no additional conical or pinch-like singularities. So that coordinate is constrained to have a particular periodicity. Yes?
So this solution reduces in the 4-dimensional case to something that has cosmological constant, or
no? They had no cosmological constant. This, I said, L is infinity. If L is not infinity, you don't get the Gucci-Hansen. L is infinity is lambda equals 0.
There is no generalization of Gucci-Hansen with cosmological.
Well, there is. This is it.
No, but in 4 dimensions.
No, not in 4. You have to have odd dimension. Well, I don't know how to do it unless you put it that way. So here are these d sigmas are a bunch of spheres, right? You actually can make this a different compact space if you want to, but this example has that. So this is the regularity condition I told you about. Normally, if F were unity, you would forget about this part and you would identify this with 4 pi. And this psi, theta, and phi would be the coordinates of a 3-dimensional sphere. But when you have F, you have a squashed sphere. And instead of getting bigger, you've got this sphere that gets squashed, but then it stops. It stops when R equals A. It's a bubble of nothing. It's a space-time in which, so here's this surface here. This is R equals A. There is nothing in here. This is nothing. There is no space in here in the sense that the signature is would be a screwball signature. It would be 3 minuses and 2 pluses. Whereas out here, the signature is minus, plus, 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 and way out here is the cosmic horizon. That's a way of visualizing what this crazy thing is. So Rick and I found this solution, and then I remembered it when Selson, another student of mine, she was looking for a project, and I thought, why don't we look at this? The geometry depends on the relative size of this soliton parameter A to the cosmological length. It does not have a black hole horizon, but it does have a cosmological horizon. This, if you like, for those of you that know what the ADS soliton is, this is like a complicated cousin of the ADS soliton. It has the same properties, except it's not ADS. There is an ADS version where this becomes a plus sign, but it doesn't have the outer horizon. So this is a single horizon solution, but the horizon is out there instead of in here. So you got the idea? Yeah.
Does it have any other particular feature? I mean, in 4 dimensions, self-duality is somehow a property of 4 dimensions.
That's correct.
So
in higher D, not that I know of. I don't know what the geometric properties are, if there's anything interesting. We didn't find this by starting with this solution. We came at it by a different route, and when I saw this, I remembered the Iguchi-Hansen thing, and that's how it happened. We didn't do it by starting here and going there. We actually had a different route to get here and discovered this was a special case. So there are 3 cases you get, depending, if you look at this, on the relative size of A to L. Either, well, one case is A is less than L, or A squared is less than L squared. So that's this thing I drew on the board. That's the soliton surrounded by a cosmic horizon. So you can use de Sitter counterterm methods, if you like, to calculate the action in various quantities, and you find that the mass of this object is given by this, which is less than the mass of pure de Sitter space, because pure de Sitter space is A equals 0. If A equals 0, this is de Sitter space. The action turns out to be this. The entropy turns out to be that. This is the same mass at space-like infinity, by the way. The first law is obeyed. It's a pretty simple and boring first law, with no change in lambda at this point. I'm frozen lambda. Regularity would force P equal 1, and the topology is R cross S3 at infinity. R times the free sphere. Case 2 is a soliton. If A squared is larger than L squared, then you have a region. It turns out you get closed time-like curves, and you've got a soliton surrounded by people that keep doing the same thing over and over again. Right? Like, have you seen Groundhog Day? You don't like movies. The rest of you like Groundhog Day, right? You ever seen that movie? You know, a guy wakes up every morning, sunny and chair. I love that movie. It's so funny. So this is Groundhog Day. And case 3 is when they are equal, and then you get a very different space-time that expands from this type of geometric structure to DS5 at late times. Now, I'm not going to look at either of these cases. They're not of interest. This is the one I want to focus on. I'm just telling you these exist. So, here's the metric. Now we're going to use black hole chemistry. So, we should have... So what we're going to do is, we took the attitude as, look, we don't really know what the mass is or what the volume is supposed to be. So let's be agnostic and just assume these relations are true and see if we can get a self-consistent solution. And then the argument would be, if we can, then we'll have an understanding of cosmic volume without any interference from the black hole volume. That's the philosophy. Well, here's the entropy you can easily calculate, and the temperature of the cosmic horizon, where K is this constant put in for convenience, because I don't want to keep writing it down. And then you find you get two cases. You can either calculate the interior mass using the methods I mentioned a few slides ago, or the exterior mass at infinity. And you find that you get plus for inside, minus for outside, plus this thing here. The volume, likewise, inside, done from the perspective of people in here, where you would stop there. Outside is out here. You get these, they're almost the same except for these sign changes. These quantities here come from the ADS-CFT counterterm. Or DS. Rather, there is a whole formalism of computing boundary counterterms in ADS space. You can take that over into de Sitter space at future infinity, and if you do that, that's what these are. So we don't know what these are supposed to be. So in other words, we have lots of possibilities for the volume and the mass. They are linked. Whatever I decide this is for the volume, it's going to affect what I mean by the mass, and vice versa. So, here are the possibilities. One is that this is 0. Why would I want that? Well, I might ask, in the limit that L is large, in the limit that lambda goes to 0, I should have a well-defined mass. Well, when lambda goes to 0, little l goes to infinity, so the only way to get that is to kill that term. That's the blue possibility. But another possibility is that I want the inside mass to vanish. In other words, I want to have people think there is no mass in here, there's only mass when you go way out there. In which case, this counter term has to be chosen like so. I could choose vanishing volume. In other words, I could say, I don't believe these things have any thermodynamic volume. I'm going to choose the counter term to kill it off. That's this possibility. Or I could say, I want the inside volume to only depend on the soliton parameter. I don't want it to depend on L. And that's this possibility. Why would I want that? Well, remember the Reissner-Nordstrom anti-de Sitter black hole, the volume of Rn ADS was equal to 4/3 pi r plus q. This has no dependence on the cosmological constant. So it's reasonable to say, look, there is a cosmic volume, but it shouldn't depend on M. And that's, oops, boy, I got my head. That's this green possibility. So what we did is so there's still ambiguity here. I think there are 4 different ways you can interpret this. You could do lots of other things in the middle, but that becomes arbitrary. These at least are motivated by various physical requirements. What about that reverse isoparametric inequality? Well, it's always violated, or rather the isoparametric inequality is always satisfied, depending on how you want to look at it, no matter what. For any, this is dimensionality, and this is the blue case, the red case, and the green. There's no point in doing the white case because there's no volume. You can't do it, there are 0. If you look at it as a function of the A parameter, rather of A over L, then you again find it's violated until A gets very close to L. Now, I have not in any of this necessarily imposed the regularity condition. The regularity condition relates A to L, and it always has, this is 6 dimensions, so in 6 dimensions it's right there. So all of these curves are a little less than 1, so at regularity or below regularity, you're always going to get a violation. So this is in accord with what we saw with the rotating case. It looks like cosmic horizons don't want to have a reverse isoparametric inequality. They want to have a normal isoparametric inequality. So I think we learned something about cosmic volume here all on its own. And that's in this paper here. All right, what about heat engines? How am I doing for time? Heat engines. Remember way back when? I said you take a hot system, let some heat go out of it, put it through a machine, drain a bit of energy, let less heat go into here, you can have this energy do work for you, provided this is hotter than that. If you want a refrigerator, put work in and then you can cool this down. So Clifford Johnson thought, hey, these black hole chemical things could be heat engines. Why not? We have a notion of pressure. So you have 2 kinds. You have a Carnot, so you plot pressure versus volume, but now you want to move the black hole around in the space. Along, let's start here. You want to start at some high pressure, low volume, and then you want to keep it, you want to expand the volume of the black hole, make the black hole bigger somehow, but keeping the temperature constant. So maybe aliens would have to be near it, throw rocks into the black hole, make it bigger, but do it very carefully so they don't heat it up. Then you want to lower the pressure. So these aliens have a cosmic vacuum energy cleaner. They suck vacuum energy and they lower the volume. Then they want to shrink the volume somehow. So then you've got to throw negative energy into the hole or something. And then you want to raise the pressure. If you do things this way, you get what is called a Carnot cycle. And in the context of this machine, the maximum efficiency you get is T2, 1 minus T2 over T1, or T cold divided by T hot. And Clifford Johnson pointed this out. You could also do a rectangular cycle. Keep the pressure constant, but raise the volume, make the hole bigger. Shrink the cosmological constant, but don't change the volume or size of the hole, and then go the other way. Actually, this arrow is backwards. This arrow should be that way. I copied that from somebody's paper, and I just noticed it's an error. I didn't actually draw this figure. So I got Clifford Johnson screwed up, because I got it from his paper. Don't tell him. Well, maybe you should tell. Don't tell him I found. Okay, so he looked at this rectangular cycle, and if you look at this, one feature it has is, remember, volume goes like R plus cubed if you don't have rotation, but entropy goes like R plus squared. So constant volume is constant entropy, which is adiabatic. So the vertical legs are both adiabatic legs of the cycle. So here there's no change in pressure, here there's no change in heat. And what he found was the efficiency was given by 1 minus the mass difference between the bottom corners divided by the mass difference at the top corners.
I always get confused with adiabatic. What is the meaning of
No
adiabatic?
heat flow. Delta Q is 0. You don't let heat in.
That's adiabatic.
That's, yeah.
And why people say that this has to be very slow?
Because any significant disturbance tends to generate randomness, which gives thermality.
Okay.
Now, these other guys, Wei and Liu, said, well, look, if we want a heat engine, real heat engines, like a steam engine from the Industrial Revolution, they actually heat steam and then it condenses into liquid and they put it around, they boil the liquid, so you're going to actually have phase transitions throughout the cycle. So they said, let's put the black hole through a Rankine cycle, which is this crazy thing. Well, crazy, it's not crazy if you were an industrial robber baron of the 19th century. You have a feed pump taking you from A to B, pumping up the pressure, and then you have a boiler that boils the gas of the liquid into steam and raises the pressure of the steam, and then you lower the pressure of the steam, at which point you've got a lot of low pressure steam that can push this turbine doing your work, and the turbine's at the bottom here, and then you have a condenser that makes the steam into liquid, and you go back again, and this blue curve is the line of coexistence. This is temperature versus entropy. So that's the steam-liquid coexistence line. And they found, well, the efficiency is basically the ratio of A, D, E, F, A on the top divided by F, A, B, C, D divided by the big one. So it's the bottom, the 1 minus the area of the bottom rectangle divided by the area of this whole thing. And they computed various measures of efficiency depending on what the temperatures were that you could start with and end with, as the case may be. So they said, yeah, you could make a black hole steam engine. I mean, how practical is that? So then Johnson and Chakraborty came along with the idea that we should compare which black holes are more efficient as engines. I mean, look, someday we all want to get rich by going into the private sector. We've got black holes to sell, and we can say, look, you want to buy a black hole? I got this really efficient one here. Right? You don't want your kids to use this. An industrial, oh yeah, it's a big man's black hole. That's what you want, right? You don't want some wimpy black. I don't want this little black hole. I mean, I want a good black, a man's black. So, they had the idea of comparing these. So let's do it for a rectangular cycle. Tend it around that and take Kerr ADS and compare it. Well, they compared a couple. Roby, Fiona McCarthy, Alvaro Ballon and me decided, let's look at this for different kinds of black holes. Kerr ADS, superentropic that I showed you before, and Reissner-Nordstrom ADS. And how does the efficiency compare as a function of the work divided by the maximum amount of work you could get, which turns out to be when the parameters have their extremal values. So there's no spin here, there's only charge. There's no charge here, there's only spin. For superentropic, you could have both. So you can see that this little box here is magnified. You see that actually the Reissner-Nordstrom black hole, for small amounts of work, right? So if you want to do a little kid's toy, you would buy a Reissner-Nordstrom black hole. It's the most efficient. But if you want to drive a Big Mac truck, you don't want a Reissner-Nordstrom hole. That's just going to be, it's going to waste, you know, your fuel bill will go through the roof. You want a Kerr ADS black hole, or maybe a superentropic one. These are almost the same. Kerr is a teeny weeny bit bigger than this. So now it depends. Look, I want something for my kids to play with. I'll get superentropic. It's the best at low work. But my superentropic black hole, yeah, that's going to power my Big Mac truck. So I'll buy that. You think I'm making this up? So then the idea was, let's do this for something more general than a rectangular cycle. Because a rectangular cycle is special. 2 of the legs are adiabatic. And maybe that biases you in favor of one kind of black hole over another. In other words, maybe if you used a different cycle, the efficiency race would compare differently, right? So that means you've got to figure out how to compute the area of a general curve in PV space. So the idea was, let's look at a circular cycle. Why is that? Well, presumably that is the engine cycle that is unbiased against any black hole. There's no adiabatic transitions, there's no constant pressure transitions. All black holes should be on the same footing for a circular cycle in PV space. Okay, that's the philosophy. So you place the center of the circle at some point, P naught and V naught in this space, and then you can show, we were able to show analytically that in the ideal gas case, the maximal efficiency turned out to be this, where P is a parameter, well, they showed this, P is a parameter. Got ahead of myself. Chakraborty and Johnson looked at this in the planar ideal gas black hole case, and they found this was the efficiency because these formulas simplify. We were able to show that for a cycle, any cycle that had specific heat at constant volume vanishing, you could get this efficiency, where these are the center of the curves. This is the normalized pressure, average pressure on the cycle. This is the average volume on the cycle.
So you take P naught to infinity, you will get the efficiency is 2.
Yeah, if you put this P naught way out there, that's right. That's right. Or V naught way out here.
The efficiency is not always less than 1.
1
minus
you get, I think ultimately if you make the volume too big, then you don't have a black hole anymore, so there are constraints on that.
Okay.
So any quantity contributing negatively to dm dv basically improves efficiency. You can write that this delta m is dm dv delta v, and if it contributes negatively, if you get minus here, then this makes the efficiency better. So we computed this for around the circle for a bunch of cases, and we found, here's a zoom in of that space. So this is the ideal gas, which basically is flat, no difference, it always has the same efficiency. This is electromagnetism, is this curve here. Curve ADS is the black curve. The green curve is, let's see, what's this curve? This curve is, EM means Reissner-Nordstrom, Einstein, Maxwell is what we use. So this is the red dashed curve, which I've lost somewhere. Maybe it's, oh, there it is. The red dashed curve is spherical Reissner-Nordstrom ADS, and the purple one is planar Reissner-Nordstrom ADS, and the green one is hyperbolic. So at low values of the work, you can see the efficiencies are different, but this curve goes up and turns over. So the planar black hole is very inefficient. The most efficient one is the Born-Infeld one. It starts off badly, but it finishes like a powerhouse. The Kerr ADS ultimately meets it at the extremal limit, but it's always less efficient. So if you want a good spherical black hole, you buy from Born and Infeld. Born and Infeld. That is the black hole that you want. And we found analytically that this actually gets to Andre's question, and I overstepped my bounds. He thought, what if these things go off to infinity, don't you get 2 pi? The answer is we found that no matter what you did for any black hole, the largest eta could be was this, which is always less than 1. And this is a theory-independent limit on black hole efficiency. So you're never, ever going to do better than that. Don't let anybody tell you otherwise. This black hole, it's 2 pi over pi minus 4 plus 0.1. Sell it to you cheap. 200,000 pesos. What do you say? Don't. There could be kids out there selling it. Be careful. So we looked at this. This is what I showed you before. This is for a 2+1 black hole where you look at different BTZ cases, rotating BTZ, charged BTZ, where there are two ways of incorporating the charge in BTZ that we found in the literature, so we looked at both of them, Q1 and Q2. One of them is just as efficient as the rotating case. The other one is lousy, it's worse than the ideal gas. We found this was still obeyed. These are checks on that process. And here's this circular thing. So all of this stuff is in this paper. The idea is the circular cycles are cycles that do not prejudice for any black hole. So now that we finished consumer reports on black holes, what about ADS CFT? This is the last thing I want to say some things about. So everybody here, or most people here, have probably heard of this famous conjecture that a gravity theory that asymptotically in I think the 10-dimensional supergravity type 2, that where you have the asymptotic structure of the space is ADS5 across a 5 sphere, it is dual to n=4 super Yang, SUN super Yang-Mills theory. That's what made Maldacena famous. And you find there is a relationship between the number of coincidence D3 branes in this theory and the Planck length in 10 dimensions and the ADS length over here. This L is that ADS length. So, variable P means variable lambda, which means variable L. And there are two ways so far that people have tried to interpret this. In one of them, variable L means variable N. And this would be the conjugate chemical potential for color in the dual theory. And that's been suggested in these papers. The other possibility is what Karch and Robinson did a couple of years ago, which is that you vary the volume of the field theory, which is implicitly in here. And it turns out that if you do that, you've actually got to vary a d-dimensional gravitational coupling, which I've put in here. Actually, L is not just related to lambda. It's related to lambda over GD. So they thought that if you want to keep N fixed, you could vary the volume of the field theory, but the price you pay is you've also got to, it turns out you've got to vary the d-dimensional Newton's constant, which would be in Lovelock language, you would have to vary alpha 1, which is what you asked about earlier. Oh dear, I didn't get the animation right here. Okay, chemical potential, CFT, let's look at the first way, which these guys have suggested. Probably a continuous variation of the number is okay. Classical gravity is the large N limit. It's similar to the thermodynamic limit. So maybe when N is quantized, you've got some different kinds of quantum gravity effects that would be interpretable in the bulk thermodynamic case. So here's the first law expressed in terms of variable N. And the number of degrees of freedom actually doesn't go like N, it goes like N squared. So these people have suggested we should really redefine U so that this is our first law. V delta P becomes U delta N, or rather it becomes a different U delta N squared. So let's look at an example of this in the context of the 5-dimensional Hawking-Page transition. ADS5, we know what the dual theory is, or is supposed to be. We don't know for sure that's it. It's still conjecture. So here's what the metric looks like, and this is ADS5. The mass is over R squared instead of R, because it's 5-dimensional. Okay? So we vary N squared. Here's 5D ADS5. And this was looked at by these guys here, Zhang, Kai, and Yu. And what you find is the thermodynamic parameters. They're easy to compute. This is the entropy, quarter of the area. This is the mass, where I've taken out this quantity m Planck tilde, which is related to the Planck mass by this factor here for convenience. And without the tilde, MPL is the 10D Planck mass. So this is proportional to the 10D Planck mass, but it's not exactly the 10D Planck mass. So what's the chemical potential? Well, the way you play this game is you compute the entropy. We know the mass. It's easily found as a quartic function of R plus. You remove R plus in favor of the entropy and L in the Planck mass to get this, and you replace L with N using that ADS-CFT relationship. So now you've got this relationship for the mass. By definition, the mechanical potential is dm dn squared, so therefore you find mu looks like that. In the large temperature limit, this thing becomes this. What these guys did was plot this function as a function of temperature, which I didn't write down the temperature here, but it's not hard to find. So you compute the temperature, and then you force this thing to be a function of the temperature, and you get this blue curve. This is mu, this is t. So down here, you have the large, out here you have a large black hole. So down here you have a large black hole. As you go up, you get a small black hole. This is the Hawking-Page transition point. So below here is the large, up this curve is the small, until you get to here. And then this curve begins to turn around in chemical potential. At this transition point, not here, this is the turnaround point, this is the 0 point, very close but not the same. And what you find is that above this, mu is positive. So they conjecture now you're in a genuine quantum regime when you're along this branch of the curve. Here you could say this is a classical regime, above 0 quantum, and in this little zone here, that's the transition.
But those are the unstable black holes, I guess.
Well,
are they unstable in this ensemble?
this is not Gibbs, this is mu, remember. This is not Gibbs.
Yeah,
so the answer is, I don't know.
Okay.
I think they conjectured it's not known because you'd have to take better account of quantum effects. Remember, these results are tentative and new. We don't understand a lot about
But
this.
if you plot the Gibbs free energy versus the delta T, you will get something different? You will get the same value?
Well, in the bulk, you'll get what we had before, right? You'll get a phase transition here from large to small. But once you're above this, right, this is all assuming mu makes sense in the dual theory. Above this, you're in a different regime that you don't see in the bulk.
I guess,
At least
I
not
guess
always.
you need corrections in G string.
Yes, that's right. That's the presumption. That's exactly that. That's the presumption. when you're in there.
This has been done also for the planar black hole?
That I do not know. That I cannot tell you. I don't think so, but maybe I'm wrong. Okay, so what about the SPA relation? That's the other approach. That's what these guys use. So here's this relationship between the ADS length and n. And what these guys pointed out, Karch and Robinson, is that in the large n limit, the free energy, which for some reason they use the parameter omega, so this is now the free energy, it's not a rotation parameter. They said that this should scale like n squared on dimensional grounds, and the CFT equation of state is energy is pressure volume times d minus 2. That's on the CFT side. So they found from this scaling relation a holographic SPA relation, and then Cedric Sinamuli and I thought, well, this should also work when you have higher order corrections, which should be associated with Lovelock gravity. So I'm going to show you what we did there because it contains their work as a special case. But they were first, as you can see. So our notion was, look, if you have higher curvature gravity, which would come from extra stringy corrections, the total free energy should be a sum of functions, each of which will have some kind of homogeneity relation. And so the coefficients in front will have the n squared, the n dependence being that of a polynomial. Now, in Lovelock gravity, the Lovelock coefficients have this dimensional scale. This should say k minus 2, I'm sorry, not d minus 2. So when k is 0, that's alpha 0, it's 1 over length squared. When k is 1, that's 0, that's the Einstein part. When k is 2, that's Gauss-Bonnet, it goes like length squared and so on. So that should be 2k, not d. So what that suggested to us is that this function should have this dependence on the Lovelock coefficients, where beta are some constants we don't know. And so this operator, if we take a derivative, a total variation of omega, that would be a d by dl derivative and a d by d alpha derivative summed over this to retain homogeneity. And this, by this relation, better look like that. So omega can be computed from this equation by homogeneity and scaling. And when you do that, you get the smart relation. And this is the Lovelock smart relation. Karch and Robinson got this term, and if you have gauge charge, you get that term. But we showed, in fact, in Lovelock gravity, if you believe that all these, if you believe in this general scaling relation, you get this. And what we also pointed out, though there's a lot more that could be done on here, is you could associate these corrections with different kinds of non-planar diagrams. So here are some diagrams on the gauge theory side. This diagram goes like n squared g Yang-Mills to the 0, which is n squared times the coupling to the 0. So this is associated with just a constant. This one is associated with n to the 0, that's L1, or the Einstein-Lagrangian. This second, more complicated non-planar diagram is associated with Gauss-Bonnet. And in general, we pointed out that these non-planar diagrams, by virtue of what their dependence is on the Yang-Mills coupling, and how the Yang-Mills coupling is related to the lambda parameter, which is related to the ADS length, we said that the kth order Gauss-Bonnet, kth order Lovelock gravity has to be related to this. So 0th order Lovelock, 1st order Lovelock, 2nd order Lovelock, and so on. Now, computing these is agonizing, I guess. That's what should happen by scaling. So, one other correspondence we looked at is Kerr CFT. So if you remember this superentropic thing, the question that came about is, suppose you start with a Kerr ADS black hole, and then you take this limit where you go near the horizon and rescale the time and distance parameters. This is what Strominger did a few years ago, to get the Kerr CFT limit. And then you could do the other thing. Suppose you take the superentropic limit. Do they commute? In other words, if I do this and then this, will I get the same thing as if I do this and then the other? Is there a sensible superentropic Kerr CFT limit? It's not obvious.
Does that commute?
Yeah, that does. The answer is yes. And the purpose of this paper was to figure out if it was yes or no. And the answer is it was yes. So here's the Kerr-Newman ADS black hole, and there's the superentropic Kerr CFT limit. So to keep a long story short, I've gone both directions. You get this metric no matter which way you go. So that means if I start with the superentropic black hole, take the Kerr CFT limit, I will get this thing in blue. If I start with the Kerr CFT limit and then do the superentropic limit, I will get this, where these parameters look like so. And then what you can show is that the central charge is given by this integral over these functions of theta. And if you use the Carty formula, you get the entropy of the superentropic black hole. So that made us happy. It should make you happy.
That's for any dimension?
This is the 4-dimensional case that we did. We did not do any dimension, but actually we did. We did do any dimension. That's right. I was thinking ahead of gauge supergravity. We did gauge supergravity, and then we did any dimension, and it works. It works.
But I think the reason for this thing is that Well, the ADS2 appears always, there is an ADS2 that controls this last result.
That's right. That's right.
So obviously, well,
That's right.
obviously if you get an ADS2 with a different radius,
That's right.
but
because of the funny topology, it just was not obvious that it worked. Herman Verlinde, when I gave a talk at a meeting he was at on the superentropic thing, and he says, what about the Kerr CFT limit? Will that work? And I said, I don't know. What do you think? He says, I have no idea. So we tried it.
because there is this vibration of the circle, maybe
Yeah, that's right.
it's different. It's
That's
not
right.
just a direct circle.
It does work, but it was not, well, my point is it's not obvious that it would work.
Okay.
And it does. So, that's the end of what I have to say in this set of lectures. Let me just summarize a few things. First, cosmological pressure can be understood as a thermodynamic quantity, and you can modify the first law to include pressure volume. That's the dominant theme of everything I've said. You have to change the Smar law, or formula, to respect scaling. When you do this, mass is interpreted as chemical enthalpy. You find that you get everyday chemical thermodynamics, van der Waals transitions, reentrant phase, triple points, and you get some more exotic things. And although we found these by varying lambda, all of these phenomena can occur for fixed lambda if it's in the right range relative to the other parameters in the problem. There are open questions. What is conjugate volume? I gave some ideas with the cosmic soliton, reverse isoparametric, but we really don't know what this quantity actually means. There's a lot more to be understood about it. Brian Dolan, I have time to talk about this, is worried about isothermal compressibility and the stability of the black holes. How do we understand that for these things? I've said a little bit in the last part about the gauge-gravity duality interpretation. This is a wide open frontier. We really know almost nothing about this. What the deuce does this reverse isoparametric inequality mean? It's clearly not fully universal, but it's also clearly means something, and we don't know what. Lovelock black holes, a lot has been done on these, some has been done on Lifshitz. We have looked, there's some things on lower dimensions that could be done. This is, I think, a big frontier. Can we use the tools here to make sense of de Sitter thermodynamics? And I gave you a bit of an idea of some things, but there's a lot more to do. The big problem here is when you have two horizons, they're in general at different temperatures, and you lose the notion of thermodynamic equilibrium. So somehow, somewhere, we've got to incorporate a notion of heat flow in general to do this. Are there other things that we've missed? Who knows? Just keep digging. So this summarizes the work of a number of people in this subject, and here's more. So closing remarks. This subject emerged as an interesting extension of black hole thermodynamics, and you get both everyday behavior and exotic behavior. But what is the underlying physics? And finally, what's it going to tell us about the quantum regime, of which I have said almost nothing in this set of talks? So there's a lot left to learn. A lot to learn and a lot left to learn from black hole chemistry. So here's the review we have. Thanks a lot for your attention, and this is a list of all the people that I worked with on this stuff. Thank you.
Okay, first of all, if there are more questions or comments or, I don't know, from the students especially. Well, okay,
Don't
there is
everybody
no pressing question. Well, okay, I have some, but it's not.
Go ahead and ask something. If you start, maybe it'll spur somebody else.
Okay, so I think, obviously I read about this stuff before, but now I know a lot more.